So I'm going to talk to you about private AI. I am the research manager for the Cryptography and Privacy Research Group at Microsoft Research. I was also the president of the Association for Women in Mathematics, which is a major professional society in the United States devoted to advancing careers for women and girls around the world. And so you can imagine I was particularly pleased to see the gender parity that you've achieved with this conference with 47% women speakers. So, fantástico. Muy bien hecho. Así debe ser. So I'm going to talk to you about our project that's been ongoing in my group for the last few years, which we call private AI. So what do I mean by private AI? AI refers to artificial intelligence. And the artificial intelligence revolution that we're experiencing in our society today is not so much about robots walking around, impersonating humans. It's more about collecting large amounts of data, which are then processed by computers. Computers that use mathematical algorithms to study large data sets and create models which can do classifications and predictions. And these models can then be used to provide value to consumers or business value to enterprises. So the way this works is that you input your data, and the computer will output some kind of recommendation or decision or classification, which is the output of some computation of some mathematical model. So the privacy problem is that you had to input your data in order to get this recommendation. So examples you should think about is when you're walking around with your smartphone and you're looking for directions or a restaurant recommendation or other more serious applications that we see coming in medicine and other fields where your data can be analyzed to give you important predictions about your health or some disease. Typical AI services are run in the cloud, and you interact with them through smart agents such as Cortana, Siri, or Alexa. And so what you can see from thinking about that is that your data is being uploaded and aggregated to the cloud by various services and companies. And then you really don't have control anymore of what's happening to that data. So you could be concerned about your privacy for several reasons. For example, these are all articles from the popular press just from last year, talking about how apps on your phone are collecting your location, something like every 4 seconds. There are a lot of different cases coming through of misuse of your data, for example, location data. IBM is being sued by the city of Los Angeles for misusing location data that was collected in the weather app when you asked for the weather in a particular location. So lots of different possible misuses of private data once it's been collected. So the important thing that I'm really concerned about is, since this is a conference about the future, think into the future. And all of your data, if it has been collected over the course of your lifetime or the last 5 or 10 years, zoom forward 10 years and think about the possible misuses of all of that data if it's been collected in the clear. It could be sold, it could be used in ways that we don't intend today. So I'm particularly concerned about privacy in the area, personal area of things like location data or my personal correspondence or my preferences, but also in things like medical data, financial data, genomic data. So all of this type of data I'm really concerned about protecting for the future and having more control over how that data is used. So to be clear, not all uses of data are bad. The machine learning models that are being developed are developed based on data that's been collected, and that can be done responsibly, and we hope to assure that it is. But what we want to do is to make sure to use all of the tools at our disposal for protecting both the privacy and the security of our data. So cryptography is a tool that provides, for example, encryption that can help to assure confidentiality and security of data. There are other techniques in cryptography that help to assure authenticity and integrity of data. But in the case of privacy, we have a new mathematical tool in the last 10 years roughly called homomorphic encryption. Now, homomorphic encryption can help protect the privacy and the security of your data while it's being used in these cloud services that I was talking about. So in order for that to happen, though, you need encryption which you can actually compute on. And so that's what homomorphic encryption means. So how many of you have heard of homomorphic encryption before? Great, so a few, but it's certainly not the easiest word to pronounce. It's not the mainstream vocabulary. But what it really means is encryption that you can actually compute on without decrypting. So in order to understand this a little better, let's turn to our friend Homer Simpson, who can help us to understand this. So let's think of an analogy. So suppose you have some gold and you want to make some jewelry out of it. But you're really not sure if you should trust your jeweler. In this case, Homer Simpson is your jeweler, and he doesn't look very trustworthy. So you might be a little worried about giving your chunk of gold to the jeweler. So what you're going to do is you're going to take that gold and you're going to put it in a locked box. You're going to put it in a box and lock it with a key. And you're going to keep the key, and you're going to give your box to Homer Simpson. Now, he's stuck using these unwieldy gloves to work on the gold and make the jewelry, and you can see he doesn't look too happy about that either. But he's going to work on, the jeweler is going to work on the gold through the box without unlocking the box, because he doesn't have the key. You have the key, and you didn't give it to him. So the point is that when he's done making this jewelry, he's going to give you back the whole box, not just the ring or whatever he made. So when you get the box back, then you unlock it, and you take out the jewelry and any gold that's left over. So the analogy here is supposed to be the gold is your data, and that could be, for example, your genomic data. You can tell so much about a person from their genome. So whatever data it is that you want to have protected, this homomorphic encryption technique, what it's going to allow you to do is encrypt that data before it's processed by the cloud service. The cloud is going to process it in encrypted form without decrypting it and give you back some encrypted output which you decrypt, which is analogous to you taking your key and unlocking the box at the end. So another way to describe homomorphic encryption is mathematically through this diagram, which basically just says that you can travel from the upper left-hand corner either way around this diagram, and you should get the same result. So another way to say this in words is that you can exchange the order of encryption and computation. That is, you can either take two pieces of data, A and B, and compute on them first, and then encrypt the result, or you can encrypt the result and then use a homomorphic encryption, and then compute on the homomorphically encrypted data, and you will get the same result. So what that allows is, that allows you to outsource computation to the cloud by encrypting on it. The cloud can compute and can return data to you, which you can then decrypt. So that's the idea of homomorphic encryption in a box. And I usually like to do a poll, so bear with me here. Please tell me, there's no right answer, who liked the Homer Simpson description better? Raise your hand. But yeah, it's a popular choice. And what about the more mathematical description? Who likes that description better? Not so many. And I always like to ask, how many people voted twice? Some people voted twice. Great. Thank you. Well, so now that you kind of have an idea of homomorphic encryption, the whole idea of my talk here is to convince you that this is a viable tool that can be used to help us as a society protect our data going into the future. So this technology is about 10 years old, as I said, and when it was first introduced, it was considered extremely impractical, 2009. 2011, a researcher on my team came up with a new encryption, homomorphic encryption solution. And since then, we worked very hard on creating practical solutions with homomorphic encryption, including, as of 2016, showing that you can actually do machine learning and artificial intelligence on homomorphically encrypted data, which was quite a surprise at the time, but many research teams have now built on that work and have improved those results to show how effectively we can actually do machine learning on encrypted data. So that's kind of the point of my talk here. And also that whenever you introduce new cryptographic technology, there is going to be a delay in the adoption of this technology because the government agencies and the industry have to get used to this new technology, and the public has to be comfortable with trusting a new cryptographic technology. Cryptographic technologies such as homomorphic encryption are based on hard math problems. So the first step is to get a community of mathematicians together who work on these problems and try to understand how hard they are computationally, so that we have a very good idea of how much computational effort it will take to break these systems. And so we've been working on that over the last 10 years, and this is a picture of the community that we've formed, which is homomorphicencryption.org community. You can go to our website, and we meet regularly about twice a year to work on the standardization of homomorphic encryption. And we have released a standard, and we're now starting to work with other professional societies to incorporate our standard into their protocols so that this technology can be more widely used. So another barrier to adoption of new technologies is the performance. So if you had heard of homomorphic encryption before, you'd probably heard that it was wildly impractical. When I started working in this area, the overhead from using homomorphic encryption was so large that executives would joke that I was competing with the age of the universe wanting to use homomorphic encryption. So in reality, though, if you look at this chart, this is actually log scale. So this is very significant. This is saying that the overhead 10 years ago for using this was roughly 10 to the power 13. So instead of doing a computation in 1 second, it would take you 10 to the power 13 seconds, which most people would agree is pretty unreasonable delay. But what we have done over time is change the way that we encode information, improve the encryption schemes, improve the algorithms for processing the encryption, and also a lot of engineering effort into improving the implementation. And so this curve shows that if you zoom forward to today, we're more like around 3 to 4 orders of magnitude worse than plain text data. So that means that something that you can process in a millisecond on unencrypted data, you can process in a second on encrypted data. And that becomes much more reasonable for many types of applications. So what I wanted to do is to show you a couple of demos. So one demo that I'm not showing because of time is actually an app that we have released, which is an encrypted fitness app. So if any of you have a fitness tracker on, you might know that the fitness trackers are uploading your location data to the cloud, and the app is giving you analysis of what you've done during the day. And again, this is an issue where all of your location data as you go through the world every day is being collected, and it could be misused. And in fact, there was a scandal where US military bases and their locations around the world were revealed because of soldiers using fitness apps, and that data was collected by Strava and it was being made available online. So that's an example of the type of privacy violation and the unintended consequences that we might face. So my team has actually built and released an encrypted fitness app called As You Run. So you can go and see that online, but I'm not showing it here today. I'd like to show you an example of using our technology in a medical application. So here you can imagine a doctor who's analyzing a patient's data and wants to analyze a chest x-ray to see what type of disease a patient most likely has, what type of illness. So what the doctor is going to do is upload the chest x-ray to this cloud service. They're going to upload the encrypted version of the image. So I'm just starting the demo now. This is a video of our software actually running in the Azure cloud. So the image has been uploaded in encrypted form, and now the result has already been returned here to the doctor, who's locally going to decrypt the result and see what the analysis is, how likely this patient is to have certain conditions. So this is, I think, an important area, health privacy. And genomic privacy and health privacy are what I've devoted a lot of my time to. And there's actually international competitions every year called the IDASH competition, Secure Genome Analysis, that teams from around the world come together to complete tasks, which are computations on genomic data in encrypted form, and compete and see what the best solutions are. So there's a lot of benchmarks out there now that will show you how efficiently we can do lots of this type of analysis on medical and genomic data. So my last demo is, again, pertaining to location. So if you are asking for the weather as you go around through the world, you may be inputting your location, such as your zip code. What happened was you put in your zip code, and then the weather service tells you, oh, it's sunny in Seattle right now. The problem being that then you're sharing your location with the service. So we have developed an encrypted version of this service, which is what you just saw running here. And only your encrypted location is uploaded to the cloud, and the cloud processes it along with its database of weather and returns to you an encrypted aggregate of a bunch of stuff, so it doesn't know what it's returning to you. And you decrypt it, and thanks to the mathematics, you magically get the weather without the cloud knowing where you are. So that's just another example of this technology, homomorphic encryption, being useful in practice to protect your privacy. So I want to thank you very much for listening and say that I hope that we will all, as a society, consider these techniques and technologies that can be used to help protect our privacy in the future. Thank you. That's it.